Thanks, Andres, and I'm really happy to be here, especially to see such a large audience of Haskellers. Let me introduce myself. I'm Stephanie. I like fancy types, probably a bit too much, but I want to talk about them today and kind of talk about what it is I like about them and why. Why dependent types? Right? And so, you know, it's kind of a strange idea. Certainly, it doesn't come naturally to take a type system from a completely different source and try to put it into Haskell. Maybe it's less unfamiliar to you now after seeing Simon's talk about linear types this morning, another idea. But I would like to do the same with dependent types. Right? And of course, Haskell is great for functional programming, right? And it's really an expression of abstraction, lambda abstraction. But there's a quantifier that's missing from Haskell, right? That's not there in the logo. And as you can see, it's kind of hard to fit in the logo. But it was one that I would like to see. So I'm going to talk about dependent Haskell, and before you ask what in the world is dependent Haskell, I'll tell you. Yeah, oh, maybe there's more. It's not one thing, and that's kind of, you should keep that in mind as I give this talk. It's not one thing. It's a lot of things that work together to make our type systems fancy, to make our type systems expressive. Right? And so what do I mean? You know, why? Why do I care about it? And so I want to motivate this talk today through an example. And that example is for a domain-specific type checker. Right? I want my type system to be able to work with me for whatever application I'm doing and help me at compile time check whatever constraints and invariants I have on that application. Right? And so the application I'm going to do today is based on regular expressions. So you can use this idea in many regular expression libraries called capture groups, where you define a regular expression, and it's kind of a simple, simplistic parser. Right? I want to both match the strings, but also pull out certain parts of the string. So for example, I have this string here. It looks like a file path. I might want to know, I might want to find some captured results in this file path that's going to tell me certain parts of it. Like maybe what is the base name of that file path? Or what is the extension at the end of the path? Or maybe what are all the directories in that path, right? So I will define a regular expression that says, look for a base name, look for an extension, look for some directories. And matching that string against the regular expression is going to give me not just does it match, but it'll also give me a dictionary that's going to tell me these results. Right? So that's what I want. That's my domain problem that I want to solve. But I want the type system to help me as I solve this problem. And how can the type system help? Well, if you look at that dictionary, right, we know from the regular expression it's going to have keys, exactly 3 keys, and no more. And so I want the type system to check to make sure that when I work with that dictionary, I only ask for the base name. I don't ask for any other keys. And also, when I work with that dictionary, look at the range of the dictionary. Right? Sometimes it might be a string. Maybe the extension is not there. Maybe I might have multiple strings. I want the type system to also keep track of that. Okay, so let's make it even more concrete. So we saw the string we want to parse. Here is the regular expression in the beautiful regular expression syntax. Right? So we start with, maybe it's going to start with a slash. Then we're going to have some directories, which are just some strings that aren't slashes, some characters that aren't slashes, and capturing it to indicate that I'm going to capture. It's a capture group. I have this question mark P notation that just surrounds a part of the regular expression, right? So this says I'm making a capture group for dir, for the directory names. And it's under a star because there could be any number of them, 0 or more. Right? And after that, I have a regular expression for the base name. It's just some more characters that aren't slashes. Again, I'm going to name it with a capture group. And then finally, I'm going to have that extension, which again is finally some characters at the end. It may or may not be there, and it's going to be named X. Okay, so that's my regular expression. And now let's see it in action. So let me switch over to Emacs. So here's my Haskell file up top. We have the regular expression right here. Trust me, the string at the top of the line is the same string I explained to you. So that's the regular expression for capture groups. Then I have the string, and the next line right here where I want to match that regular expression for paths against my particular string. That's going to give me this dictionary called dict. And then once I have that dictionary, I want to access the different parts of it. Right? I want to find out what is the base name of that string. So if I ask for X, I should be able to get the base name. And after Y, I should be able to get the list of all of the directory names. And if I ask for Z, I should be able to, it should tell me, yes, there was an extension, and here's what it is. Right? And I want you to notice a few things, right? So Haskell is able to infer the types of X, Y, and Z. They have different types. Right? So X is a string, Y is a list of strings. Now let's do one more thing. Let's add an access to F, which was not in my regular expression. So here, I said, up in the regular expression, I said capture, dir, base, and ext. There's no capture group named F. So I'm going to save and then reload. Let me try to move this up. I know it's hard to see the bottom, right? And so I get a type error, right? This is a type error I want to get, right? Because I did something wrong. The type error is identifying a bug, and it says, hey, Haskell exchange. I couldn't find a capture group named F. Here are the ones that I could find, right? And it tells me exactly what my problem is. Okay, so that's what I want to do. That's how I want the type system to help me out for this particular problem. Okay, so how do we do that? And of course, the answer is dependent types. But let's dive in, right? Because dependent types kind of sometimes takes on this magical quality. Of course, all of our problems will be solved if we only had dependent types. And that's not a good enough answer for me. I want to know concretely, how do we do this? What is it about dependent types that allows us to write code like this? And so I'm going to walk through some parts of the implementation of how I wrote that little library and show different features of GHC that are working together to give us something that looks like dependent types. Right, so, and I've kind of separated this into 4 distinct capabilities that we're getting from a dependently typed language. Right, so if we are working in a dependently typed language, these are things that we want to be able to do. Right, and I'm going to walk through them individually and kind of show you how they come into play in this particular example. So let me just start with the first one, right? And that's being able to program with types, right? We have domain-specific applications. We have libraries for our domains. We can program those libraries. We should be able to program the types that go with those libraries. Right, and so how do we do that? And where does that come into play, right? Well, one part of what we wanted to do, how does it work, right? Well, we defined this regular expression, and the regular expression has a type. Let's take a look at what the type of that regular expression is, right? So the type of the regular expression here, this RE, that says it's a regular expression. But the rest of this is some information that tells us more information about that regular expression. It's not just any regular expression. It's a regular expression that captures 3 groups. And there are the names of the 3 groups, base, dir, and ext. And then also, not only that, but how many strings are we going to get out when we capture that, right? We should see exactly one base name in something that matches. We may see many directories. We optionally will see an extension at the end, right? And so part of it is being able to make this connection from this data here to some information that we can use later. Right, so how does that work? Well, right, so this expression is, oh, and I just want to say this big part here, I'm going to call it an occurrence map. It's telling me how many times those capture groups are going to occur inside one of my dictionaries. And it's just using this promoted data type. It's just a data structure that has 3 different variants. Right, so how does this work? Right, so well, the first part, you could probably guess from the template Haskell. We have to do a little bit of template Haskell, and all that is doing is processing the regular expression syntax. It's not doing anything with the types, right? It's taking those characters and turning them into a sequence of function calls that correspond to sort of the parsed version of that syntax. Right, so the very first part, we're going to use template Haskell for compile time parsing. Right, and then we're going to use these smart constructors for our regular expression abstract syntax type. And these smart constructors, that's the second part. They're actually going to compute what that occurrence map should be. Right, so the second part comes from the type functions that appear in the types of those constructors. Right, so you saw before, we're going to parse a regular expression to applications of these constructors that look like this. They have types that some of them look like this. So, for example, the regular expression that is just a single character, it doesn't capture anything. So its occurrence map, it's just an empty list. It doesn't capture anything. But for some of the other ones are much more interesting, right? So for sequential composition, we do one regular expression, then we do another one. What does it capture? Well, it captures everything in the first one and then everything in the second one, right? And so we have to figure out what the first one captures, we have to figure out what the second one captures, and then we have to run a type function that merges those results together. For a star, we figure out what could be captured under the star, but then we have to say, well, everything that could be captured under the star could be captured 0 or many times. So we need to convert that and say we're going to do some repetition here. And likewise for this one, this is saying, here's where I'm marking a capture group that's happening. We're merging in. We've seen exactly this key with whatever else we've seen. All right, so let me boil down what do these type functions look like? Right, if in Haskell we write type functions using something called type families. Right? It looks a lot like functional programming. Right? So R star, we need to calculate from this occurrence map. What is it? It's just a list of pairs of strings and occurrences. So we can write a function, just a simple recursive function, that works over these lists of strings, or the list of pairs. So if we're not capturing anything, we still aren't capturing anything. Anything else, whatever the occurrence was before, we're going to force it to say we could see it potentially many times. Okay? So being able to express that is a key importance, and being able to say that relationship, we needed to be able to do a little bit of functional programming here. Okay, so I'm going to do a little more demo just to convince you that this all works. Let me reload now that get a version that type checks. Right, so here, let's just see here. So here is some, I've stripped away the template Haskell layer. Here we're just using these marks and stars. Any is a regular expression that matches any single character, right? And what I want to show you is that Haskell, come on, load, can even infer these types. Right, if you see if you can see that here. So I asked for the type of that particular regular expression, I'm marking a capture group for any number of arbitrary characters. I get one occurrence of the A capture group. And similarly for RB, right? And then once I start putting them together, you might try to think, well, what is going to be the occurrence map if I have an RB followed by an RA? What will Haskell infer, right? So let's ask, right? And it says, look, there was one A and one B. Right? You might notice it sorted these occurrence maps, right? It has to keep track of it and merge. If it sees that one part captures an A and another part captures an A, it has to merge them together. So it has to line them up. So it sorts them to keep track of it. Let's do another one. Let me do this one right here, example 3. All right, so what is this regular expression? Right, we are capturing an A, and then follow that, we're capturing a B, and then we're going to iterate that any number of times. So what should its type be? Let's take a look. Right, so here you can see we've run that type level function over, right, when we put that R star around it, we run the type level function over the occurrence map on the inside, and that's turned all the onces into manys. Because now that we're under a star, we could capture multiple results. Okay, so we want to be able to compute our types. Okay, next part, what else do we want to do? Once we can compute types, we want to use that type information that we've computed in a useful way in our program. And so what I'm calling that, the next step is called index types. We want to use that type level information to constrain our data. Right, so we've calculated that the dictionary that we get from the result of doing the match has this type. So that we create the regular expression, we match against it. Our output type is a dictionary, and the dictionary is indexed with the same occurrence map that the regular expression did, because we know it's an output of that particular map. And when we access parts of the dictionary, we're going to be using the information in that index to be able to access various components of this dictionary, right? Just so that we can make sure that even though those components might have different types, and we can also check to make, we can also produce type errors when those components aren't there, right? And so how can we do that, right? You saw this in the example. How can we make this connection between what the type of the dictionary is and how the type system is allowed to use it, right? So one important ingredient is being able to constrain exactly what that dictionary is with that type, right? So when we have a dictionary that has a type like this, we know a lot about it. We know, in fact, it has to look like this, right? It has to be, maybe the strings are different. Maybe we don't know how many strings are in this list, but we do know that it has to start with a string for the base name. Then the next entry in that dictionary has to be a list of directories. And then the last entry in the dictionary has to be some sort of maybe value for the extension, right? That is determined by our definition of the dictionary type. It's going to use that index to control what kind of values we have, right? And I want you to notice a few things, right? So the keys, the actual base, dir, ext, they don't appear in the dictionary value at all. Well, you know, it's a dictionary, but we're not storing the keys. But we don't have to. We know what the keys are when we compile the program. Why do we need to have them around at runtime? Right? We already know what they are, and we already know where in the dictionary we're going to store the base name. So we can just erase those keys. We don't need them, right? Because we're going to be able to figure out, using our compile time information, how to access the different parts of this dictionary. And if that access fails at compile time, that's how we can get that error message. Okay, so we constrain that value, and we're going to constrain that value using a gadget. a generalized algebraic data type. And what this is being able to take the parameter to the data type, this occurrence map, it's the parameter for this data type, and have it vary based on whether we have an empty dictionary or we're extending our dictionary with another entry. So if we have an empty dictionary, then we're going to say that parameter can only be the empty occurrence map, right? It's a dictionary that doesn't have any entries in it. So we're not going to be able to look up anything from it. Otherwise, if we have some kind of entry for a particular string key and for some occurrence value for it, then the index for the dictionary should say exactly that. This is also enforcing the order that things appear in the dictionary, because the order of the tuples in the list is going to control the order of the entries in the data structure. Right, and what are those entries? Right, when we have an entry, we're giving a string to say what its key is. We're giving this occurrence to say what type of should we be storing for this entry. Right, so for example, if we have an entry for the extension, it should be a maybe type. Right, so our definition of the entry type has to figure out from this particular occurrence what Haskell value should we expect. And here we're going to use another type family. Right, so we're going to create our entry that has this string, the symbol, the type level string, and an occurrence, right? But the actual data that we're going to store in this entry, it's actually going to be decoded by this type family, this function, right here, right? That says that, if we only have one, we're going to return a string. If we have many, we're going to have a list of strings, and so on. Right, so again, having the information around in our type system gives us a way to characterize our data structures in an interesting form. Okay, so we've seen being able to write type functions to compute data in our types, being able to use that data to constrain our data structures. Now we're going to get to something that people consider kind of the heart of dependent types, right? So far, I haven't even mentioned that pi at all, right? Well, here's where pi comes into play, right? Being able to use data both at runtime and in types, right? So, and we need to do this here too. So think about this. So if I have a dictionary, the type tells me what it has to look like. So it might have to look something like this. I can print it, right? I didn't show you this in my demo, but I can print it out. And if I print it out, I get something that looks like that. Now, what's interesting about this string that I get from printing my dictionary? Well, how about one thing? Where did example come from? It's not stored in the dictionary. This string right here that is part of my output of print, it's coming from the type. Base. That string. Yeah, this is stored in the dictionary. This is not stored in the type. This is stored in the type. Yeah, so base, dir, and x are all stored in the type. And not only that, what I do to print things out in this component, in that entry, and in that entry, and in that entry, I have to do different things to convert them to strings too. I have to know how to marshal them. Right, so this is where pi usually makes its appearance, right? So, because we want to use things in two ways, and that's the key part of the pi binder, is that it's giving you access both at runtime and compile time to a particular argument. Right, so here's a way that we could show these entries to be able to convert them to a string, right? If we're going to show a whole dictionary, we have to show all the individual entries. And if we had pi in Haskell, this is the type we would give it, right? So it takes a key, or the string for the key. It takes a string for the occurrence type, takes an entry that's indexed by that key and that occurrence type, and it's going to give us a string, right? And the string it's going to give us is whatever the name of that key is and whatever the data associated in that entry is. And so you can see, so I'm not going to show you this, but I will show you show data to show the data, this is really funny, because we need to know how to, we're going to get different types of data every time, right? So this O, it's either going to be once, opt, or many. We want to just show it, but show is overloaded in Haskell. And so Haskell needs to know which show we're going to use. And it doesn't know which show we're going to use until we do this pattern match. So when we say, OK, we're showing data that is described by once as its occurrence, then Haskell can figure out, oh, we need the show for strings. And if we're showing the data that could optionally appear, then we need the instance of show for maybe strings, and so on. So it looks like this pattern match is useless, but this pattern match is providing a lot of information to the type checker to help it resolve the type classes. OK, but we don't have pi. Right, so what do we do instead? Right, so in Haskell, to write this code without pi, we do a technique that's called singletons. We create a data structure that reflects compile time data into runtime. And it's called a singleton because it matches up one-to-one with the compile time data. For anything of a particular singleton type, we know exactly what it is. It's so constrained, there's only one value that can have that type. And so we need singletons for the keys, for those strings, and we need singletons for the occurrence type. And so when we have show data, we're actually going to pattern match on the singleton values that just directly mirror those occurrence types, right? And that's going to allow us to dispatch to the various show operations. And what are those singleton values? Well, it kind of looks like this. It's like a GADT where singleton, it's indexed by occurrence, but you can see that, right, S once, the data constructor for once, right, it has this type. So if we see something that has type sing once, we know it has to be this data constructor. And if we see S once, we know that whatever this index is, it has to be once. So this is how we can pattern match on things that are at the type level using this technique. OK, last bit, right? So fourth bit is doing some kind of proofs, right? And dependent types, they come from type theory, which is really a foundation of mathematics. It was there to be able to express why things are true the way, how do we know what is truth? What kind of proofs can we do? What is a consistent logic? And so there's got to be some kind of proofs involved here. So let's take a look at the kind of proofs that we have to do when we are doing dependently typed programming in Haskell, right? And really, they all boil down to equivalence proofs. We are putting programs in our types. We are type checking. What is the essence of type checking? It's comparing types for equivalence. Now that we have programs there, we need to be able to compare those programs for equivalence. All right, so where does that show up in this example? Right, so let's boil down. So I showed you earlier that we parsed to some constructors that we use to create these regular expressions. These constructors, they're called smart constructors because they kind of wrap up the actual constructors of my regular expression type. And why do I have them? Well, I have them so I can do a little bit of optimization as I'm wrapping up, right? So for example, if you have a sequence, right, one regular expression after another, and the first regular expression is just the empty regular expression, you can drop it, right? You don't need to represent that in your data structure. That's an isomorphism of regular expressions, right? So we want to be able to, there's a couple of different optimizations that we could do as we build our regular expressions that can make our library more efficient. Now, but when we do these optimizations, they have to type check, right? Because we say sequence has to have this type, right? Whatever the first one captures, whatever the second one captures, we need to be able to merge them together, right? So this one captures nothing, that one captures something. So we need to have, we have this little proof obligation here that says when we merge nothing and something together, we get something. Right, so that's the example of the kinds of things we need to prove when we're doing this kind of programming. Now, in this case, we're really lucky because our definition makes it really easy for Haskell to prove this. If you look at the definition of how merge works, the first case, it's just a function, and the first case of that function says if the first thing is nil, then do the second thing. So Haskell will do this proof automatically for us. Right? We don't have to do anything special. Okay, what about this one? Right, so for star, here's some optimizations I can do when I'm constructing a repetition regular expression. Right? If I'm just putting a star around empty, star empty is just the same as empty. Doesn't change it, right? And so to do this line, I need to know that repeating empty is equal to empty. That's also easy. That's not a problem. But the next line is the one where we run into trouble. So what do we need to be able to type check this line, right? So I'm putting a star around something that is already a star, right? And that's redundant, right? 0 or many times of 0 or many times. That's the same as just a single star, right? So my optimization leaves off one of the stars. And for this to type check, it doesn't, right? I get a type error if I just try to do this, right? And Haskell gives me an error message. And it tells me exactly it shows me exactly the constraint it doesn't know how to prove, right? It says that I couldn't deduce repeat s equals s if I know that s is repeat s1. Right? Maybe I can rewrite it a little bit, right? Basically, it's trying to prove this, that if I repeat something twice, it's the same as doing only repeat once. Right? This is not, if you remember the definition of repeat that I showed you before, this is not something that falls out of just evaluating repeat. It's something that's true about that definition, but it's not obvious to GHC that it is true, right? So what do we do, right? And this is where, if you were in a dependently typed language like Coq or Agda or Idris, you would have to write a proof. You would go to the definition and prove this as a lemma, and then when you get to that part in your code, you apply that lemma to prove to the type checker that this is a valid optimization. Right, I'm going to do something a little bit different. I'm going to use a type class, and what I'm going to do is I'm going to define a type class that captures exactly the occurrence maps that have the properties that I want, and then I'm just going to constrain all the occurrence maps everywhere to have those properties. So it's a little bit indirect, right? Come on. It's a little bit indirect. Somehow this is not reflecting the same as my screen. The best part. Sorry about this. We're going to need a proof, but. Okay. This one. I'm a little concerned that doesn't go away when we unplug it, though. Okay, so all of the code is online, as are the slides. Though I've been slightly editing them all day today, so it's not quite the latest version of the slides. But the code is all there if you go to my GitHub. let me see if I can describe to you a little bit about what we need. So we need a type class that holds for exactly those occurrence maps that have this property. I'm going to call that type class WF for well-formed. These are the occurrence maps that I like. Then I'm going to add that constraint everywhere to my data structures, to my functions, right? And so what that means is whenever I program with this constraint, I have this property that I need. And so here, in this function here, it's going to have an extra WF constraint for S. It's going to have an extra WF. That's not the right one yet. It's going to have an extra constraint for S. So when we get to that line, we will know that this is true in the context automatically. And so we don't even have to explicitly apply our lemma. The Haskell type checker will say, well, I need to deduce that, and my context says I have that, so we're done.
Can you give an example of an occurrence map that doesn't have that property?
So it turns. Yeah. I told you this was a bit roundabout, right, Simon? I'm going to say this is going to be true for, I want this to work for all type classes such this holds. But it turns out that all occurrence maps have this property in my instances for occurrence maps. So I need to prove that so that I can use these functions that are constrained by that type class. So I need to know which some particular occurrence maps have that property. So I can give an instance for nil for the empty occurrence map. Yes. Right here. Right? I can say, OK, I'm going to make an instance for this particular occurrence map. And so Haskell will say, OK, you can have that instance as long as I know this holds. But this something, if we put in nil for S, this is something GHC can do. Right? It can then repeat, and get to nil, and then reduce it again, and reduce it. And then this is a proof that is easy enough for GHC. Right? And then we need to do another case. And we say, OK, well, maybe our occurrence map wasn't empty. Maybe we actually had some key here and some value and some more. Well, we get to assume that the rest of the list is well-formed. We just need to know that this particular one. And this matches our structure for how repeat works. So again, this is something that GHC can do automatically. It can verify that this instance declaration holds. And I don't have to write any more code. I'm a little bit lucky here that it all works out. So this is not a technique that will work in general, but it works for our purposes, what we needed it to do here. And as I said, the nice thing about it is that when I go down to where I need that property, I have it automatically, right? Haskell looks for this particular property, and it finds it this time instead of giving me a type error. Now, you might say, OK, so that's for our star. What about your other functions? Well, like our seek and our alt for alternation, right? So it turns out there were 3 properties that I needed for this library to be able to do the optimizations that I did, right? So one of the optimizations I did was if you were alternating 2 things that were exactly the same, you didn't really need to add an extra alternation. But in order to type check that alternation, I needed to know that alternating 2 things is the same was the same. And then here's another, this is from another one. So I had to add a couple more properties to what it means for a occurrence map to be well-formed. But I didn't have to change my proofs. Because again, these are all proofs that GHC could do by just very simple, straightforward induction. OK. So this is what I needed for this example, right? So I should ask you, are we working with a dependently typed language here, right? I don't really care what you call it. I just care what it does, right? The types are pretty darn fancy, right? And it has these capabilities, right? It can do what we want to do. So I want to look a little bit more closely at what enables things like type level computation. What can we say about Haskell's interpretation of this capability, right? So to do this type level computation, we have lots of great stuff, right? We can represent data, we can write functions, we can use type operators to make those functions look like terms. We're not restricted in how we do our type level computation. We could also use type classes to do some computation for us. We have full flexibility, so this is even a little bit more permissive than many dependently typed languages because we have type and type, or we have undecidable instances that allow us to not worry about termination when we are doing our type level computation. We have one big missing piece, though, right? We don't have the way to have anonymous functions at the type level. And it's not so much of a semantic issue, it's more of a type inference issue. It's very difficult to bring in these anonymous functions to the way Haskell's current type inferencer works. It's just putting them in groups. I don't think they have a... This is more functional programming. This is more logic programming. This is things that are not available in other dependently typed languages, unique to Haskell. Maybe, like there are languages like Cayenne that had type and type and various other ones, but Haskell has that ability now. Okay, so yeah, we have type level computation in Haskell, quite a bit of it. What about index types, right? I showed you how we can use gadgets, and we have a very rich notion of what we can index those gadgets. And we can make them even more flexible because Haskell has the ability to even quantify over constraints. The way Haskell does gadgets is a little bit different than indexed data types in dependently typed languages like Coq and Agda and Idris. The biggest difference that you might notice is Coq and Agda and Idris have support for co-inductive and inductive types, because in that context, they need to show that everything terminates. So they need to restrict how you use your data structures to enforce those termination guarantees. We don't have any termination restrictions in Haskell, and so we can't really express in the type system when we expect data types to be only used in an inductive fashion or in a co-inductive fashion. Okay, what about this? We kind of have OK support because I showed you how we could use GADTs in the singletons library that Richard Eisenberg and others have developed, automates some of the boilerplate that goes along with using GADTs. But it'd be better if we had a real pi type. And Richard and I are working on what do we need to do to be able to add a real pi type into GHC. And again, the hurdles are integrating with the type inferencer. There are some semantic questions about how does pi interact with all of the other features of GHC, like levity polymorphism or roles or unboxed types, right? Now linear types. So there's work to do, but I think it's optimistic to think that it can be done. Right, and then last, what about these proofs? And here we're kind of all over the board, right? Because GHC was not meant to be a proof language. We can hijack it by, sometimes when we resolve type classes, we're going to be doing some proofs. Sometimes when we write functions, the definitions of those functions are going to give us the equations we want. Sometimes we can code up proofs using gadgets, but then we kind of have to run them if we really want to make sure they work. This is something that GHC offers that other languages don't, the ability to add in new solvers into the type system to be able to automatically construct those proofs in a very flexible way. What we're missing here is really a termination checker, right? So that only comes into play for the sort of using gadgets to represent proof witnesses for propositions and inequalities that we might prove by hand. But these other forms, I think it's really exciting that we have an opportunity to not just be limited by the way that say, Coq or Idris or Agda are developing proofs, but explore what really is one of the hardest part of dependently typed programming in lots of different directions. Okay, so I hope I've convinced you that this is exciting, right? That we've got a lot of fun, fancy types to play with in Haskell, and it's not, when we're talking about dependent Haskell, we're not just talking about these pies, right? And all of this, the examples that I write, right, I'm getting inspiration from these dependently typed languages, but I might be putting them into Haskell in a different way because Haskell is a different language. And I think that's really good, right? Because we're in a different point in the design space. So we have a real opportunity to learn something new, right? So, because we're working in GHC's rich environment, we can really learn new things, new patterns of dependently typed programming, new interactions with our type checker, right? And so I think it's really exciting to do this kind of work. And I'm just going to end there, and I think we have a little bit of time for questions. So here's some links to the code and where the video will be.
Thank you.
Thanks.
Okay, yeah, so we still have about 10 minutes left for questions, so go ahead.
Hello, hey, here. Here
Bright
I am,
light, yeah.
Thanks. So in your experience writing these kinds of programs with GHC and sort of dependently typed style programs, how often do you end up using undecidable instances? Is it like always, or can you get by with functional dependencies in some cases, or what's your experience?
So you saw that big list of language extensions? I usually just cut and paste it from one file to the other. So I don't rarely try it without undecidable instances. So I can't really answer that question.
Okay. Personally, I never understand why people are worried about undecidable instances, but I think, yeah, I see you, but there's a question back there, which was first.
So it's two short related questions. One is the fact that we have type families and things like symbols, which are replicating term level things like strings and functions. Is that an artifact of the complications of implementing real functions from types to types? And the other question is there any intention to unify these two separate term level versus type level languages that we have in Haskell?
I'll answer your second question first. And I would dearly love to unify these two languages, right? And mostly because why do we have completely different syntax for writing a functional program that happens to be in the type level from a functional program that happens to be at the term level, right? They're both capturing the idea of a relationship between these inputs and these outputs. I want them to have very similar semantics. And I want them to have very similar syntax because I think the language will be more uniform. There are hurdles for unifying them together, mostly due to syntax, right? It's a pretty big syntactic change to make this unification. And part of this is there's a lot of Haskell code out there that takes advantage of the fact that they are different syntaxes. Like think about all of the data types that pun, where you use the same name for the type constructor and the data constructor. Right? If you're going to glue the syntaxes together, you're going to glue together the namespaces. How do you resolve those issues? And it's not quite clear to me what we can do. Maybe we have to do something that's not going to be so backwards compatible if we're going to have that full uniformity. Can you restate your first question again?
Oh, my first question was, we have, say, type families, which basically mirror functions at the type level. Question was if that was an artifact of being complicated to actually implement real functions. So is that why there had to be another construct instead of just...
why are type families not functions to begin with?
Yeah. That's an example.
Yeah, I'm not sure I know the answer to that. Ask Simon.
I don't know how to answer that either. So I think it's partly that the things grew sort of incrementally that way, but I think also just promoting arbitrary functions that might have list comprehensions in them means that the type checker is going to need to execute those list comprehensions, right? And also terms contain type class resolution. So now we're going to have the type class system happening at compile time with kind level type class. My brain is too small to accommodate all of this, but I Stephanie is dragging me, very slowly but
Richard's
surely.
brain is not too small, and Singleton's does all of that.
Yeah, that's right. So somehow we're doing it through Singletons.
Yes.
So maybe the light may dawn.
Yeah.
When
So if you are
explain it to me.
intrepid, you can try it out.
My role is to be slow and steady.
You mentioned over there. You mentioned a couple of times that you were lucky in your example, like all proofs were really simple and stuff. What happens when you're not lucky, and how do you overcome that?
If you are not lucky, you have to restructure your proof in some other way. So I listed several different ways of doing proofs. One way I didn't list, but perhaps I should have, is unsafe coerce. And here I'm being serious, right? Because there is a property that this expression is equal to that expression. Maybe the type checker can prove it, but maybe you have to go into a different framework and do those proofs in another framework. And you do it on paper, or you model Haskell's type system in Coq and do the proofs there. What doesn't matter so much that the type checker does it. What matters is that the proofs are true, right? And it would be much better if the type checker could do it, and you could do it all in one framework, but you shouldn't be so worried about putting an unsafe coerce in your code.
So I could add to that, because I think of a type system as kind of like an attention localizing device. If there's a bug in your program, instead of being anywhere in your code base, you want to look at the unsafe coerces. If the places you're unsafe doesn't mean unsafe. It means I, the programmer, am undertaking the proof obligation here. So it localizes and makes explicit your proof obligations, and that's fine, right? Having no types at all means you have, massively greater proof obligations. Having locally, local dynamic typing like that in a way, it's just saying, well, I undertake that.
These are my assumptions that
you
I'm
might
working
prove it
under.
separately, or you might just say, just believe, I'm sure it's true. And but I have a question as well. So, which is this, that always bugs me about dependently typed programming. In your example, you had your regular expression was part of the program.
Yes.
Right? It was part of the source code of the program.
Yes.
Now I want to take your program and I want to read in the regular expression from a file.
Yeah.
Now what do I do?
That is not, I didn't work out this example here, but that's generally not a problem to read it in from a file, right? I mean, because if you even look at my code, I started with a string, right? Maybe I did the parsing at compile time instead of runtime, and so there's a little bit of dancing to figure out how to do runtime parsing as well. It involves existential types, so that you can, because you don't know the type of the thing that you're going to get out. And so you have to say, well, whatever type I get out, it's this type, and then I'm going to work with that.
But
now, if you don't know that at runtime, you can't, if you don't know that at compile time because you're reading off a string at runtime, you can't do the same kind of compile time resolution because you don't have the information then. But what you can do is say, okay, read this out from disk, verify it has some of these properties. Right? You can check the information that comes out, right? And that will give you a richer static information that you get.
So right at the beginning, you had the example where you said, oh,
Yeah.
let's have Y, and it has type. It was get field, @ base, right?
Yeah,
And it had type list of string. Well, if you don't know what the regular expression is, of course, you couldn't even type check Y.
Yeah, exactly.
And that would be bad, wouldn't it? That's what isn't. I mean, so if you can't do that, then what's left?
Well, I mean, you could.
That was the point, wasn't it?
Perhaps you, like, when you're working with a regular expression, right, and you might want to push all of your dynamic check into one point, which is make sure the regular expression captures these groups, right? And so you can start with any string that you want, dynamically do that type test, and then after you've done that, then you can access X and Y all you like. Right, and you know you wrote down X and Y, so you know you know what you need from that regular expression. So as long as you can express that dynamic type test, which you can.
If I might follow on from that, suppose I have a regular expression in a file, and I check. I know that I need to use the base field of its dictionary.
Yeah.
So I check that it has a base field.
Yeah.
But I don't check what other fields it has.
Yes.
So then at compile time, I don't know, because I don't know where the base fields are going to be in that dictionary. Because I don't know what the other fields are. So at that point, do I not have a problem?
Okay, so in this example, you probably do have a problem because the order of all the fields is fixed, right? And so if you don't know the order, you don't know how to access it. Right, so you have to at least be able to check what the prefix is. You might be able to write a check that would work for just partial information. Then we're going to get in a situation that's kind of like row types, if you've seen sort of extensible record type systems. Right, we run into a lot of the same issues there. If you want to allow reordering and say, I don't care what it is, I just need to know it has a base field and there could be an alpha field in front of it, then you have to make your accessor functions a little more general so that they can maybe bring in the description of what those fields are so it knows exactly where in the structure to find it. Right? But then you're pushing into more dynamic checks instead of static checks.
Okay, so we're unfortunately out of time. Please remain seated for the time being, but let's first thank Stephanie once again.